Okay, so we talked about parallel lines early in the school year. We were talking about slopes, and we said if you have two lines that are parallel, they have the same slope. Okay, so we know that. It's one thing that we know, that we've learned just this year. Parallel lines, they have the same slope. Okay, so that's one thing. I'm just gonna put a fancy little line under my title. Alright, so parallel lines have the same slope. That's one of the pieces of information that was new to you this year that you learned this year. Okay, when we're solving systems of equations, we're looking for where do these two lines cross. That's the whole purpose of solving systems of equations. Where do they have the same x and y value? And that is the one and only spot where two lines cross. Well, parallel lines are special. Why are parallel lines special? Because they never cross, okay? So if you were to try and solve a system of equations with two parallel lines, you're going to get something that makes absolutely no sense, okay? And so I just want to show you the special case of solving systems of equations with parallel lines. And you actually have two different types of parallel lines, okay? So we're going to deal with both of those separately. We have what's called non-coinciding parallel lines. Non-coinciding parallel lines, you can think of them as like the train tracks. Okay, so what do I mean by the train tracks? They're parallel lines, they go forever and ever.
In a straight line.
Well, everything is in a straight line here. We're just dealing with linear equations. But they go forever, side by side, never crossing. Never cross. Okay, so if you picture train tracks in your brain, they're side by side, they're the same distance apart the whole way, they never ever cross. Okay, that's a non-coinciding parallel line. So what happens if you have two non-coinciding parallel lines and you try and solve the system of equations? Okay, so let's look at that. So here's an example I'll give you. One of my equations is going to be in general form, or almost in general form. It's going to be 21x minus 3y equals negative 3. The other equation is going to be in functional form. Y equals 7x plus 5. Looking at these two equations, there's nothing that tells you that you've got two parallel lines here. Okay. If they're both in functional form, and it's really easy to see the slope, right here we got the slope is 7. If they were both in functional form, it would be really easy to go, oh look, they have the same slope. So they're parallel lines. But if they're given to you like this, this top equation here that's in general form, it's not easy to see if it's got a slope of 7. You could figure it out, but you're not going to do that for every system of equations that you're given. You're not going to go through the hassle of finding the slope for the two equations and making sure, okay, are they parallel or are they not? You're just going to go about solving them. Which method would you use to solve these two systems of equations? You've got one in general form and one in functional form. It's going to be comparison, substitution, or elimination.
Substitution.
Substitution. Whenever you have one equation that has one of the variables isolated and the other one with the two variables on the same side, that's a substitution method question. So we're going to solve using substitution. And nothing at all here is going to be different. Nothing is going to be different from what I'm doing here from what you did before, except for the outcome, and you'll see what I mean by that. So we're going to do this example here. So we're going to take our top equation and we're going to sub in our y. So minus 3 times 7x plus 5 equals negative 3. And we're just going to solve the same way we would normally solve. So we have 21x. I got negative 3 that I got to multiply by my 7x, and I got negative 3 I got to multiply by my positive 5. So negative 3 times 7x is negative 21x. Negative 3 times positive 5 is minus 15 equals negative 3. 21x minus 21x,
0.
0x. So I have negative 15 equals negative 3. Does that make any sense whatsoever?
No.
Does negative 15 equal negative 3?
No.
No. Okay. If you complete solving systems of equations for two equations and you end up with an answer that is nonsense, which in this case doesn't mean like your grandma's telling you, oh, you're full of nonsense, you're just making things up. This means that it's absolutely not true. It does not make any sense. All right? You know that your two lines were non-coinciding parallel lines. The other way to look at it is there's no x's or y's left. You haven't solved for anything. Your x has disappeared. Normally when you do this, the whole purpose of doing this is to figure out what x equals. And then you use that to figure out what y equals. Well, your x disappeared on you. So your first little thing that you're going to remember for non-coinciding parallel lines, or the key here, is that if your variable cancels out, and I'm not talking about addition method where we're purposely trying to cancel out one of them to leave us with just the other one. Right? If there's no variables left, so if your variable cancels out and you are left a nonsense answer, you started with two non-coinciding coincide. Ooh, that's bad. Two non-coinciding parallel lines. Okay, so everybody sees how this answer here doesn't actually make any sense, and you've lost both your x's and your y's are gone. Are there any questions about anything that happened in this little solving here? Why this disappeared or anything like that? Okay, we see it. Good. We're just going to look at the other type of example. The other type of parallel line. If our one type is non-coinciding, what do you think our other one is? Coinciding. So our other line type that we're going to deal with is coinciding parallel lines. Parallel lines. These are parallel lines that have the same slope. All parallel lines have the same slope, but these also have the same y-intercept. And if you were to graph these lines,
Are they on top of each other?
yeah, they would be directly on top of each other. They would actually look like one line. Look like one line. So when you think about it, as we've solved systems equations, usually we're looking for that one spot where the two lines cross. It's one coordinate. Non-coinciding parallel lines, those lines never cross. They just go on forever and ever and ever. You could think about coinciding parallel lines as crossing all the time. They're constantly touching. Okay? Let's look at what that actually does in terms of our solutions. Okay? So, here's our example. We have the equation negative 3y. Oh, sorry, no. Negative 3x minus 3y equals 12. And y equals negative x minus 4. So those are my two equations. Again, I've got a functional form and a general form, or a functional form and a form where my x's and my y's are on the same side. They don't, right off the bat, looking at them, they don't look like the exact same equation, right? They don't look like they necessarily have the same slope and same y-intercept. As a matter of fact, we'll find out if you did mess with them and you rearrange them, you would see that they have the same slope and the same y-intercept. But you wouldn't notice that right away. So we would just go about solving these using comparison method. Okay, so we're going to go about solving these using comparison method. So we're going to go to our top equation and rewrite it. Negative 3x minus 3 times negative x minus 4 equals 12. Multiply by my negative 3 into my brackets. Okay, so I've got negative 3x plus 3x plus 12 equals 12. What happens with my negative 3x plus my 3x?
Cancel.
They're gone. And I'm left with 12 equals 12. Does that make sense? Does 12 equal 12?
Yeah.
Yeah. Okay. It still isn't what we expected to happen. We expected to end up with x equals something. We expected to solve for an x coordinate. It's not what happened, but in this case, we weren't left with a nonsense answer, we were left with an answer that actually makes sense. And so that's the biggest difference between these non-coinciding parallel lines, where we end up with a nonsense answer and our variables canceling out, and our coinciding parallel lines. For coinciding parallel lines, we still see our variables cancel out. So once again, our variables disappear. Out. Oops. Our variables cancel out, but the expression we're left with makes sense. Okay. Now these two things are not huge pieces of the puzzle. They're not things that generally will make up a big section of your exam or anything. But there's always a chance that you're going to get given a couple equations and that's what's going to happen. And so it's important to realize that it can happen and what it means. Okay, so that when you're doing a test and you get 15 equals 15 all of a sudden, and you get, okay, I'm going to go back and check that and check your work and it all worked, you don't think, oh, this is a stupid question, it doesn't work. But what that means is that you just happen to be given two equations that are, in this case, they would be coinciding parallel lines if they had 15 equals 15 as your solution. Okay, are there any questions about that? No? So this is another one of those things that it should find a little corner of your memory aid and you should know where it is and you should know how to use it. shouldn't occupy too much of your time, but it's something that you should make sure you remember, because it will show up either in a short answer or a multiple choice question generally. This doesn't really fit into a big long answer. It doesn't really fit into a situational problem so much, but short answer multiple choice, it's definitely something. Coinciding, non-coinciding parallel lines could definitely show up.